This video is about polyprotic acids. You should already be able to write mass expressions, which are the Ka expressions, and calculate the pH of weak and strong acids and bases. And at the end of this video, you should also be able to calculate Kas of weak acids and predict the pH of polyprotic acids, meaning acids that have more than one hydrogen. We've been avoiding them. So the question of the video is, what is the pH of rainwater that has a dissolved carbon dioxide concentration of 1.4 times 10 to the minus 5? So if I know exactly how much CO2 is in the air, I can figure out what the pH of that acid rain would be. So let's start from here, calculating the Ka from a pH. If the pH of a 0.1 molar solution of H₂SO or formic acid is 25 degrees Celsius is 2.38, we want to know what the Ka or how weak that acid is, right? So what we could do is start by setting up a Ka expression. The hydronium ions times the formic ion divided by the formic acid is how we always set up our Kas, right? The ions divided by the acid itself. We can also find the hydronium from the pH. And we know that for every hydronium, there's also going to be its conjugate given, because these are usually both X. So if you look at the pH and it's 2.38, what we know is 10 to the minus 2.38 is how many hydroniums we have. So I'm going to plug in our icebox. We originally had 0.1 molar of the solution and no ions. We shifted to the right as usual, and these are our equilibrium conditions. But from this information, 2.38, we know how many hydrogen ions we have, 10 to the minus 2.38, or as we solved to be 4.2 times 10 to the minus 3. If that one's 4.2 times 10 to the minus 3, so is this ion because they're both X. What we can do now is plug it back into the Ka. A key thing here is not to forget to subtract it from 0.1 in case that number was not small. In this case, it doesn't matter because 0.10 minus 0.00042 is not going to change 0.10. But you should always just check in case because it could in these type of questions. So we're going to plug it into our Ka expression and solve, and we get 1.8 times 10 to the minus 4th. So if you know the pH of a substance, you can work backwards and get a Ka just the same as usual. You're still writing a Ka expression, you're still doing icebox, you're just solving in the opposite direction in the Ka expression. So let's do it one more time. What's the Ka of a 2 molar acid with a pH of 5.45? So if the pH is 5.45, that means the hydrogen concentration is 10 to the minus 5.45. And the Ka is always written as the ion squared divided by the molarity. So if I just plug that in, the ion squared are 10 to the minus 5.45 squared, right? I don't have to actually change it in my calculator if I don't want to. I can be completely lazy about it. It's not my answer. I'm going to divide by 2 because that was the original molarity. Once I solve that question, I can get the Ka, 6.3 times 10 to the minus 12. So this is a shortcut version of what we just did in the previous slide. You don't have to write iceboxes, although they're really helpful organizational tools for most students. You could avoid it if you want to. But I don't recommend this version. I'm just saying that for the people who are advanced in math and you understand what's going on, you can show as little as this much math. Now let's talk about the polyprotic acids. Polyprotic acids means there's more than one hydrogen, like H₂SO4 or H3PO4. If the difference between the Ka of the first acid and the second subsequent Ka values is 10 to the third or more, the pH usually depends on only the first time it loses its hydrogen, which is why we've been treating them that way. We've been saying, hey, ignore all the other H's, just look at the first H, how much of the first H comes off. Like if the first H comes off like almost 100%, the second H is actually going to be bound a lot stronger. And therefore won't ionize as often, and will probably ionize less than 5%. So it really won't change your answer that much, but we're going to prove it by doing a bunch of calculations. So here's some examples of some polyprotic acids where they have more than one H, and you can see that they gave you multiple Ks. They give you K for each H that comes off. For ascorbic acid, the first H comes off pretty weakly at 8 times 10 to the minus 5, and then the second one comes off even weaker at 1.6 times 10 to the minus 12. Almost doesn't come off at all, but you're seeing how weak that is. And as you go through, you can see there's as many Ks as there are H's. I want to point out the sulfuric acid. The H₂SO4 is one of our strong acids, and that's why the Ka1 is written as large. It's probably 1. It's going to come off all the time. And then the second hydrogen comes off less, as weak. So the second hydrogen always clings on a little bit stronger than the first time, right? You can see every time the Ka decreases across. So let's calculate the pH of a 0.1 molar sulfuric acid, assuming it only ionizes once. So this is what sulfuric acid looks like. If I take off with just one H, what would the pH be? Well, we know sulfuric acid is strong, so for every H₂SO4, there's going to be one H coming off. And so I could just negative log the 0.1 and get a pH of 1. What I want to now think about is if it assumes it fully ionizes. You have to treat this as two different H's. The first time it ionizes and then the second time. They don't come off at the same point. But, I mean, even so, if you assume that all the hydrogens come off, for every 0.1 molar here, you're going to also need 0.1 molar there. So that's why we're doing a pH of negative log of 0.2, one for each hydrogen. And now we see the pH went down to 0.7. If you actually measure H₂SO4 though, its pH is a lot closer than 1 than it is to 0.7. So we have to figure out what's going on. The second hydrogen must not be coming off as much. So let's calculate the actual pH of 0.1 molar sulfuric acid, and notice they gave you the Ka2 because remember the Ka1 came off 100% of the time. So again, the first time is strong acid, it fully ionizes. For every 0.1 acid you put in, you get 0.1 of each particle. And therefore, what we're going to do is now icebox the second ion. So if we take that H₂SO4 minus that's left over, for every 0.1 that I have, I might get 0.1 H ions because I already have those from before. Notice this is a different icebox. 0.1 H₂SO4s and 0.1 from before of H's. There's no sulfate ions at first, so that means the change will shift to the right because we have to form sulfate ions to get at equilibrium. And then at equilibrium is 0.1 minus X, 0.1 plus X, and 0 plus X. Now what we're going to do is plug it into our Ka2, which is X times 0.1 plus X divided by 0.1 minus X, and that's the Ka2 given. This is really ugly. You can take time to cross multiply and distribute out. But because the Ka is pretty small, we can ignore the plus X and the minus X. The change. Only the changes. Because if you ignore all X's, you'll have nothing to calculate. So if I do that, now it just looks like 0.1 times X divided by 0.1. The 0.1s will drop. And now you'll just get X equals 1.2 times 10 minus 2. This actually happens every single time. The second X, or the ion that you don't know, is always equal to the Ka of the second time it loses its ions. So now what we have to do, if we want to figure out what our pH is, we have to just plug it back in. 0.1 that we had gotten from the first ion, plus 1.2 times 10 minus 2 that we got the second time we ionized, which is a lot less, is 0.112. And then if we wanted to know what the pH is, we're just going to negative log that value. Notice the pH is 0.95. Which means that when I just thought of it before was pH of 1, when you just have 1, that's a really good estimate for this. 1 was what if we only lost 1. 0.95 is what we really get. And then remember if we lost 2, we got 0.7. See how off that is? So we are not actually losing 2 hydrogens. We're only losing 1 and a partial of a second. Let's try that again for H₂SO3. You notice H₂SO3 is a weak acid because it's less O's. And therefore it gave you 2 Kas. That means we'll have to do, unfortunately, 2 iceboxes. So the first time it loses its ion, it was 0.1 molar. It loses its ions and it shifts to the right like a normal icebox. The X is 1.7 times 10 to the minus 3 when you solve for X by doing icebox. So the second time it loses its ion, it started as H₂SO3 here. There was 1.7 times 10 to the minus 3 of them. But remember, there's also 1.7 times 10 to the minus 3 of the hydrogens. I know this is a little off. Let me just fix it really quick so it doesn't look so ugly. Right? So there you go. Maybe it's a little easier to read now. Okay. So what we're seeing is it's going to still shift to the right, and you can still get the 1.7 minus X, and 1.7 minus X, and the X here. We plug it into our icebox, products over reactants, and again, we can ignore the plus and the minus X, the change. So if I ignore those plus and minus X's, I get 1.7 times 10 to the minus 3 on the top and the bottom of this fraction, which means it cancels out. And the second X is equal to, hey, the Ka2. So again, if you want to write, instead of writing all this, you can just say the second X is always equal to Ka2. And in that case, now what we have to do is just go back to our icebox. The hydrogens are equal to the first hydrogens, X, which is 1.7 times 10 to the minus 3, plus the second hydrogens, which is 6.4 times 10 to the minus 8, the Ka2. So now what we do is we add them together and then just negative log the addition, and we get 2.77. I guarantee we will practice this more in class. It's nothing to be worried about. It's just 2 iceboxes. So back to the question in the video. If we know that the dissolved CO2 in the air is 1.4 times 10 to the minus 5 molar, and the Ka of this acid, or H₂SO3, where it came from, is, sorry, my volume went down. We're back up. 4.3 times 10 to the minus 7, we should be able to calculate the pH of the rainwater. So here's the acid it came from. Remember, your CO2 came from the breakdown of carbonic acid. And the carbonic acid is in equilibrium with its ions. So every time you have an acid, you actually form H ions, but maybe very minutely since the Ka is really small. And this is the original concentration, 1.4 times 10 to the minus 5. There were no ions to be present at first. We're shifting to the right to form ions, and we're writing as an equilibrium. When we write our Ka, it's x squared over the concentration equals the Ka. We cross multiply and square root to find x. Once we find the x, we can go back and find out how many ions there are. So we can just negative log that x value and get 5.61. Now I know what the pH of the rainwater is. It's not 7 because it's not normal water, is acidic rain, right? Not only that, but notice that I did not ionize the second hydrogen because as we saw in the previous polyprotic acids, the second ion hardly ionizes. And if I wanted to do that, I would have needed to know the Ka2 and done another icebox. So at this point, you should be able to calculate the Ka of a weak acid and the pH of any polyprotic acid.